At Lockheed Martin, we're on a mission. Your mission. Not just the next mission, but the one that's 2 steps ahead. The one that depends on solving problems before they happen. Our mission is to prepare you for the future by engineering advanced capabilities today, so that you can protect what matters most. That's why we've not only taken the lead in hypersonics, but we're helping you integrate that technology faster than ever. It's why we're not only developing the laser weapon systems you'll need, but deploying them in the field. It's why we've coded cyber readiness into everything we do. It's why we created Orion, the only spacecraft that can take humans to the moon, Mars, and beyond. Why the next generation fighter is ready to help you protect the generations to come. And why we've already built autonomous technology and artificial intelligence that advance human ability. The multi-domain battle space of the future is already here, and there's no time to waste. No time to play catch-up. New age threats require new age capabilities, and that's why, at Lockheed Martin, our mission is to build the integrated solutions you can depend on. Because the world is depending on you.
Thank you for joining today's presentation. I'm Scott Swan, the Simulation and Modeling Lead at Lockheed Martin Aeronautics Industrial Engineering Department in Fort Worth, Texas. Today I'm going to walk through some of the technical details of a project my team, with the assistance from Simio's solutions engineers, are currently working on to capture some of the complexities we face when modeling large component assemblies. I will start off with a little background of the project, dive into a bit more detail on the solutions, and close with a demo of the model so you can see how everything came together. A little background about Lockheed Martin Aeronautics. The operations at the Fort Worth facility include machine shops, painting, composites, 2 bend and weld shops, component assembly, and flight operations. Component assembly is the area we're going to focus on in this presentation, as they have some rather unique characteristics. The first of these being the significant number of man-hours, in some instances thousands of man-hours, that are expended while a single component is in a build area. While this alone doesn't sound all that complex, when you add in the fact that the staffing levels in each build area change month to month, modeling a build area can become complex rather quickly. Further, certain shifts may be more efficient than others due to experience levels. And finally, there are times that components may be forced to move or pulse out of a build area before all work is completed in order to make room for an incoming component. The problem statement that the modeling needed to address is a combination of these unique characteristics I just mentioned. Specifically, a lot of things can change in the many weeks or months' time that a component spends in a build area. These might include changes to staffing levels like I previously discussed, or number of workers, quality assurance delays, or rework, or part shortages, all of which may add time. And finally, contract priorities may put a higher priority on completing one component over another. Modeling the component build area as a simple server doesn't fully capture the behavior that is required for us to have visibility into our operations. Ultimately, the objectives of modeling the component build areas was to, 1, quantify the number of workers needed by shift to finish work within a designated tact, and secondly, to reduce the number of pulses that result in traveled work. The basic model only consists of a source, 3 servers, 1 for each build area, and a sink. We've taken a table-driven approach with most data residing in tables, with the objects referencing these 6 data tables, which I will now explain. The first table is the stations table, which we use to auto-create the servers and set capacities. Next is the load schedule table, which is an arrival table used by the source to introduce components into the system based on their scheduled start date. This table also contains information to set the initial state of the model, or WIP. The EAC table contains man-hours for each component for each build area, as well as additional man-hours that can be added to each component if it is known that additional work for a particular component is required, such as QA or rework. Next is the equivalent head schedule table, which includes information on the number of workers on each shift by month for each build area, as well as information on the maximum number of workers that can be assigned to work a single component. The current resource table pulls the current number of workers on shift from the equivalent head schedule table. This table also contains information on the shift efficiency. Finally, the resource work schedule is used by the table-based work schedule and provides the dates and times each worker pool is on shift. To meet the objectives of having a model that can quantify the number of workers by shift that minimizes traveled work, the model needed to include the following features. First, it needs to capture the initial state of the system, which components are in which build area and how much work is remaining on each one. The model then needs to have the ability to handle changes to staffing levels on a month-to-month basis, like we previously discussed. Next, it needs to allow for the movement of components from one build area to the next. We call this pulsing or pulsing of the line. And since there is no space between build areas to stage or store components, pulses may force incomplete components to exit a build area before all of its work is complete. If a component is pulsed out of a build area before completing all of its work, we need the model to quantify and record these unworked hours. And finally, the model should have the ability to assign workers to components differently than the standard first come, first serve approach, such as front loading or level loading of resources on a component, as well as the ability for components to begin processing even if it is unable to seize all of its resources. To make all of these enhancements to the model, some of which were very challenging, we partnered with Simio support and their solutions engineers to work through many of these solutions. We would not have been able to do much of this without their support. For the first enhancement to the model, we needed to populate the model with the components that are currently in the system on the day that we initialize the model. Due to the length of time that some components spend in a build area, setting the model to initial conditions was preferred over a long warm-up period. Also, not only do we have to ensure that in-work components are in their correct build area, but we also need to ensure that only the remaining hours are attributed to each component's processing time as well. For instance, if a component that has a total of 500 hours of work in the J860 build area, but has already worked down to 100 of these hours by the time the model is initialized, we would want only 400 hours of processing time to be assigned to this component in J860. Since all of this information is in the load schedule table, we simply searched the table for rows that were designated as WIP components, created the corresponding entities, assigned the remaining hours to the entity state, and transferred these entities to the designated build area. Over the contract period of a program, it is not uncommon for the staffing levels to change. Typically, this is due to the program starting at a slower production rate and then ramping up to a faster rate as the program matures. Therefore, staffing levels at the beginning of a program may be lower than they would be in the middle or the end of a program. During some portions of the program, it is not uncommon for staffing levels to change monthly. To model the monthly changes in the number of resources, we used a table that contained the number of resources available by shift for each month and a state on each resource that would automatically update the number of resources at the appropriate time. This was accomplished by having the server select from a list of resources with only the on-shift resources being available and setting the off-shift rule to switch resources if possible to allow resources ending their shift to stop work on a component and resources coming on shift to start work. Pulsing of the line is where things started to get a bit more complex. When a component initially enters the system from the source, or when a component completes all of its hours at a build area, a pulse or component move from one build area to the next can occur. Whether this pulse occurs is dependent upon available capacity at not just the next downstream build area, but at subsequent build areas as well. I'll walk through a couple of examples to help illustrate the details of this logic. When a component leaves the source to enter J860, the component looks to see if there is available capacity at J860. If there is capacity, it enters and starts processing. Simple. If there is not available capacity at J860, then it checks to see if there is available capacity at the next downstream server, in this case J850. If there is capacity, a component that is not yet 100% complete at J860 is interrupted and forced to move to J850. This in turn allows the component coming from the source to enter J860. If there is not available capacity at J850, then a check is made to see if there is available capacity at the next downstream server, in this case J830. If there is, a component that is not yet 100% complete at J850 is interrupted and forced to move to J830. This in turn allows a component to move from J850 to J830, a component to move from J860 to J850, and finally the component leaving the source to enter J860. However, if there is no available capacity at J830, this creates a no-pulse situation, since components cannot leave J830 until work is 100% complete. In this case, the component trying to enter J860 is forced to wait. A similar situation occurs when a component completes all of its work at J860. Capacity is checked at J850 and then at J830 to see if capacity is available, or if components need to be forced to move early to allow the component completing J860 to continue. The final scenario is when all build areas are at full capacity, a component is in the source's output buffer waiting to enter J860, and a component completes processing at J830. The component exiting J830 will free up capacity, and a component that is not yet 100% complete at J850 is interrupted and forced to move to J830. This in turn frees up capacity in J850, and a component that is not yet 100% complete at J860 is interrupted and forced to move to J850. This in turn allows the component that is in the source's input buffer to enter J860 to start processing. All of these forward-looking checks from J860 to J850 to J830, and the backward-looking checks from J830 back to J850 and then back to J860 are performed using multiple decide steps, interrupt steps, and release steps as shown in the bottom right. When a component is interrupted or forced to pulse before it completes all of its processing at a build area, as detailed in the previous slide, the unworked hours or traveled work needs to be accounted for. We built the solution to handle travel work in two ways. We can either apply the traveled work to the next downstream build area, or we can simply record how much time was left when the component was interrupted and report these hours as a performance metric at the end. For the most part, the solution was the same for both approaches. We used the Save Remaining Time property on the interrupt steps to save these hours in a state column in the EAC table. Depending on how we wanted to handle these hours, either report as a performance metric or apply them to the downstream server, the data could then easily be accessed from the table. The last enhancement that was required was the ability to change the way that resources could be allocated to a component. In general, the more resources that are assigned to a component, the faster it will be worked, although there is a maximum number of resources that can be assigned due to space considerations. The two resource allocation strategies that the model needed to be able to handle were front-loading of resources and level loading of resources. Front-loading of resources is the default way that Simio and all other discrete event simulation languages assign resources to entities, basically a first-come, first-served approach. Although we had to allow for components to start processing even if they were assigned fewer than the maximum allocation of resources. So in our situation, the first component that enters a build area is assigned the maximum of the number of resources needed, or the number remaining, whichever is less. The second component that enters is then assigned the maximum number of resources needed, or the number remaining, whichever is less. This continues until all resources are allocated or until all components have the maximum resources needed. In the example with 10 components, 42 resources, and a maximum number of resources per component equal to 5, the first 8 components get 5 resources, or the maximum number of resources that can be assigned to a component. The 9th component gets 2 resources, which is the number of resources remaining, and the 10th component gets 0 resources. With this allocation of resources, the first 8 components will start to work down their hours with 5 resources each, while the 9th component will work down its hours more slowly since it only has 2 resources, and the last component will not start processing since it doesn't have any resources allocated. When level loading resources, resources are spread as evenly as possible across all components. In the example with 10 components, 42 resources, and a maximum number of resources per component equal to 5, all components get at least 4 resources, and the first 2 to enter are allocated 5. So all components will work down their hours, with the components with 5 resources each working them down a little bit faster, since they each have more resources than the others. The main difference is that all components will start processing when level loading, rather than in the front loading scenario where some later arriving components may not immediately begin processing upon entering the build area. To accomplish both front loading and level loading, we used a very lengthy expression in the units per resource property to determine how many resource units each component should seize, based on the front loading or level loading rule and the number of resources available in the current resource table. Secondly, we used the same expression in the resource efficiency property to divide up the total required time to each allocated resource. Finally, the resource efficiency factor was then considered to adjust the time to complete the expected man hours based on each shift's efficiency. I know that was a mouthful, and I must admit that we relied heavily on Simio's solutions engineers for this solution. Now that I've explained how we implemented these solutions, I'll show you how it all came together in the working model. In the property window on the right, we have many of the model settings that we can change. The capacity of each build area, whether we carry forward traveled work to the next station or merely record it as a performance metric, whether we are front loading or level loading resources at each build area, and the maximum number of resources that can simultaneously work on a component. When the model is initialized, you'll see components that are already in work immediately populated into the respective build areas. Additionally, the number of resources assigned to a component is shown above each component itself. Below each build area server, a status label shows the active resources that are currently working each build area. Further down, each build area's first, second, and third shift resources, as well as the overtime resources, are shown as being on or off shift. When on shift, each resource shows the total number of resources available to be assigned, the number that have been allocated, and the number remaining to be assigned. The state of the system shown right now indicates that component 1 has arrived to start J860. However, J860 and J850 are both at full capacity. J830, on the other hand, is only using 2 of its 5 positions. This will cause a component in J850 to be interrupted, which will then cause a component in J850 to be interrupted, and both be sent to their next downstream build areas, allowing component 1 to load into J860. As I step through the model, you'll see the components turn red, indicating that they have been interrupted before completing all their work, and subsequently move to the next build area. At some point, all build areas are at full capacity, and component 4 arrives to start J860, as shown in the current view of the model. Because all build areas are full, and because components need to be 100% complete at J830 before leaving, we are in a no-pulse situation, and the component trying to load J860 will wait until a component completes J830. Eventually, a component completes J830, This allows components to flow downstream, allowing component 4 to finally enter J860. Right after J830 frees up, you may have seen the first shift go off shift and the second shift resources allocated to each component. After that, second shift finishes and third shift starts work. This type of behavior repeats throughout the course of the model run. I'll now run the model without the breakpoints so you can see it run uninterrupted. That completes my presentation on how we have modeled the complexity of large component assembly at Lockheed Martin Aeronautics. As I mentioned earlier, much of this would not have been possible without the help and assistance of Simio's support personnel, as well as their solutions engineers, especially Ryan Luttrell and Adam Sneath, who we worked closely with to arrive at some of the more complex solutions. Now I would be happy to take any questions. Thank you.
So Scott, great presentation. We do have a lot of questions from the audience, so I'll just jump right into them. For your model, what were the objectives of the model? What are some of the use cases completed with this model?
Sure. So, like I said, the model is still in work model and is basically built as a prototype that we could apply the solution to other projects. So it wasn't a standalone model that we were going to use to answer a specific question, but is more of a prototype approach that we could implement into other solutions. Some of the use cases, however, uh, are very similar to what the demonstration that I showed. We have components that are moving in that we have a specific. We have components that have multiple steps that need to be moved from one build area to the next, and as all of those hours are working down, they continually pulse through the line, so to speak. So really any place that we have a situation where we have a handful of hours and need to be worked, but we have more incoming components that are going to force things to move down the line, we could apply this solution.
Okay. And jumping more into the model and the model data, how often do you run this model, and is data imported automatically each time you're on the model?
So what we would be doing again right now, it's kind of a prototype model, but the intention is, yes, we would import the data with some bindings. We probably would do it on a monthly basis. So we would have updated data on the number of shifts, or sorry, not the number of shifts, but the pool of workers by shift every month as those change. So we plan on running the model probably on a monthly basis.
We have some questions about the kind of your object choice. Why did you use the resource object instead of the worker object in your Simio model?
Really only because we didn't necessarily need to show workers moving from one location to the next. We just needed to show that there was some sort of constraint involved. That's the main reason. We could have used workers, however, we chose resources.
Of the model expansion requirements you mentioned, what were the most challenging to implement?
Definitely the most challenge, and I'm glad Adam's. I can see Adam here as well. I'm glad he's here because probably the most challenging was the one that Adam and Ryan helped, which was the level loading of resources. Um, that one I mentioned in the presentation that it required a lengthy expression, and I think that's an understatement. Uh, Depending on, I guess specifically the level loading of the resources, making sure that every resource gets a certain number of resources, kind of spread out, as close to a level as possible. That, the pulsing of the line, there were some challenges involved with that. However, most of that we were able to get worked out internally at Lockheed, but the level loading and the leveling and loading of resources and the efficiencies was the most challenging.
Scott, a follow-up question on that. Can you elaborate a little bit on the process of verifying the model behavior as you add those more complex details?
Sure. Yeah, that was a very lengthy process. We went through and we had to go through and make sure that every time when a plane is pulsing, that it's, depending on what type of resource allocation strategy we were looking at, we were making sure that when the component was pulsing, that it was the correct number of resources were being allocated. I don't know if you noticed in the demo, as soon as a component moves into position, it doesn't necessarily always get its current allocation of resources, because you're not going to pull people off of, at least our approach is, we're not going to pull people off of one component and immediately send them to a different component. But that is going to happen more on a shift change basis. So, a lot of those changes of, of the level loading and all that, and the allocation of resources occurred between shift changes, between first and second shift, second and third, and so on and so forth. But yeah, the
Okay.
verification of it was challenging.
Yeah, it's great to see how you used the model animation to help with that and the various labels you applied to help visualize it. I'm sure you'd also use the model trace to really dig into some of the
Definitely.
grittier details. So that was
Definitely.
cool to see. Yep.
And Scott, I want to, as we come to the closing of this this session, I want to thank you again. Lockheed now has participated in 5 out of 5 as Simio thinks we had. So thanks so much for your support, and thanks again for a great presentation. Have a great rest of your day.
Great. Thank you very much, Eric.